In the discussion of my lectures on quantum mechanics, in continuation of this particle in 1D box, part 2, lecture 11, I shall try to give emphasis on these comments for this normalized wave function of the system. And the normalized wave function of the system is psi n x root over 2 by L sin n pi x by L. For a particular system of this particle mass m and the length L of this box, psi n x depends on the quantum state n and the positions of this particle x. And I can show here the number of discussions on this, on the basis of this wave function of the system. First one, the system is non-degenerate one. Non-degenerate means every state of this, every quantum state will have a particular value of this wave function and this energy value and this energy value. Say this is the quantum state to n equal to 1, psi x equal to root over 2 by L, and instead of x, instead of n, we shall put here 1 and sin pi x by n, and energy also h square divided by 8m square. So for this second state, n equal to 2, it has also a different wave function and different energy value than this one. And this sort of a system we call the non-degenerate systems. And the number 2, the wave functions are orthogonal to each other. The different wave functions for the different states of this system are orthogonal to each other. Means these states, the wave functions represent, are independent to each other and also non-interacting. As we have seen, it could also be shown which wave functions are the orthogonal to each other. And for this system, it is integration 0 to L psi ni state, and x is the function of this psi is a function of x, and this is psi nj x dx, and this must be equal to 0 for these two wave functions to be orthogonal. Say whenever we are doing this mathematics, then 2 by L root over 2 by L square of 2 by L and sin n pi x by L and sin nj pi x by L and 2 dx. And this sine functions are converted into cosines. 2 is taken inside this integration and having this one, this part and this part. And whenever we are doing this integration and putting this limit, each of the integration will be equal to 0. And in this case also, if we consider that, if we consider this psi 1 and psi 2, whether these two are orthogonal to each other, then instead of this one we can put psi 1x, instead of this one psi 2x. Again it could be shown these two equal to 0. Means these two states are independent and non-interacting. And this third point I shall discuss, this psi n x versus x plot. X plot. Already I have told this psi n x for a given quantum state depends on this value of x. Say for quantum state n equal to 1, this psi 1x equal to root over 2 by L into sin pi x by L. and whenever this x equal to 0, this is psi 1 0 equal to 0, and psi 1 L by 2 here, L by 2, this is the maximum. When we are putting this x equal to L by 2 here, this one equal to 2 by L, and psi 1 L equal to 0. That means this plot psi and x versus x plot will be like this. And when this V for the quantum state, n equal to 2, this psi 2x equal to this one. And again when psi 2 0 means at 0, x equal to 0, this is 0, and psi 2 L by 4th here, it is the maximum root over 2 by L, and here L by 2 equal to, then psi 2 equal to 0, and here it is the 3 by 4th means here it is negative root over 2 by L minimum value, and psi 2 when L, then it is equal to 0. So this plot will be like a wave. And this, besides these 2 points, in this point, this psi n x equal to 0 means it is the nodes of this state. So whenever we are putting this quantum state n equal to 3, then sin x 3 equal to root over 2 by L, sin 3 by x by L. Instead of n, we write here 3, and psi 3 0 equal to 0, psi 3 0 equal to 0, psi 3 is L by x equal to root over 2 by L maximum, and psi 3 L by 3 equal to 0. This is also nodes, and psi 3 L by 2 equal to minus root over 2 by L minimum, and psi 3 2 by 3 L equal to again 0. This is also node, and here this psi 3 5 by 6 L equal to maximum root over 2 by L, and sin 3 L here also 0. So this curve will be like this, and here these are the two nodes, this one, and the number of nodes, actually number of nodes equal to n minus 1. For this state 1 node, for this state 2 nodes, and so on. If we actually closely look to this picture, then psi 1, this is psi 1x and psi 3x, these two are symmetrical. Means if we keep a mirror at this middle point of this box, then one half will be a mirror image of this other half. So the wave functions for these odd quantum numbers are always symmetrical, while wave functions for this even quantum number are anti-symmetrical. As here it is anti-symmetrical, and this is the conclusions that I can draw for this wave function psi x versus x plot. This is the normalized wave function for this system. Means any information or any property of the system is mysteriously hidden within the expression of these wave functions. If any information is not available from this wave function, then it is believed that that information might be absent for this system. Now I shall try to give a plot of this probability density versus x the probability density is psi n x whole square equal to, or modulus square of psi n x equal to 2yl sine square n pi xyl. And if we plot this probability density versus x plot for different values of different quantum states, then for this quantum state n equal to 1, psi 1 x square equal to 2yl and sine square n equal to 1 pi xyl. And when this x equal to 0, this is 0, x equal to l by 2, this is maximum 2yl, and x equal to l, again it becomes 0. So this plot will be like this. For the quantum state n equal to 2, psi 2x equal to 2yl and sine square, and instead of l we shall write 2 pi xyl, 2 pi xyl. So again for this quantum state 2, this when x equal to 0, it is 0, x equal to l by 4, here putting the values, x equal to l by 4, maximum 2 by l equal to l by 2, 0. This is also the node, and when x equal to 3 by 4 l, again equal to maximum 2 by l, and this, and psi 2 l, and when x equal to l, again equal to 0. So in this case there is one point where this and this point l by 2 at this middle point of this box, so there is no chance for the particle to be found at this point. For the quantum state n equal to 3, so modulus square of psi 3x equal to 2yl sine, instead of sine square, and instead of n we can write 3 pi x. So in this case also, when x equal to 0, it is 0, x equal to l by 6 equal to 2 by l, and x equal to l by 3, again 0, this is the nodal point, and x equal to l by 2 by l maximum, this x equal to l 3 by l, again 0, this is also another node, and psi x equal to 5 by 6 l, when l by 2, again maximum, and at this end when x equal to l, it is 0. So this plot will be like this. So, and whenever a it is seen, some we can get some special comments on these pictures. Say one picture is that at this middle point the probability density is maximum, means a maximum chance for the particle to be found at this point. Here at this point, at this point, here at this point, at this point, at this point. Though the chance is varying, chance for the location of this particle in this box is varying point to point, still whenever we are trying to measure the location of this particle or position of this particle within the box by any instrument, then we can get only one position, one location for the particle to be found. This is the measurement paradox. As when all the chances becomes one when we are doing the experiment for finding this particle within this box, and this is also one paradox. And the second one, say this one, at this point the probability density equal to 0, means no chance for the particle to be found at this point. Here maximum, here maximum. So it is again one question coming, how the particle is moving, executing to and fro motions without touching the middle point. This is also another question comes up from this picture. Then the third one, Bohr's correspondence. Whenever A, you can see, whenever A is increasing, quantum state is increasing, the distribution of the locations of the particle within the box becomes uniform, more and more uniform. When n is very large, then these curves will be like this, means the total uniform, complete uniformity occurs for this location of this particle in this box. It is the similar to the classical mechanics. Classical mechanics states that every locations for the particles to be found are equally likely. So n equal to, whenever it is very large, this term, this quantum mechanics results corresponds to the classical results according to the Bohr's correspondence principles. Again, for this macroscopic bodies, say macroscopic bodies, for macroscopic bodies, En equal to n square h square divided by 8n l square. So n square equal to 8m l square into En divided by h square. So for the macroscopic bodies, n is very large, and so h is very small, square again smaller. So this one will be very high. So for this hard quantum state, when n is large, the macroscopic bodies automatically will follow the classical mechanics, and every location will be equally likely for this macroscopic bodies. For the calculation of the physical properties of the system, first we shall have to construct one quantum mechanical operator for this property. Then this operator, by treatment on this function, we shall get this value or magnitude of this property. And several properties by this way I can show how these are calculated. One, energy eigenvalue En for this system. This Hamiltonian operator, it is the operator for this energy, and psi nx will give you the minus h cross square by 2n into d2 by dx square into this wave function, And whenever we are doing this double differentiation of this sine function, we get this n square, y square, h cross square, twice ml square into psi x. So it is the eigenvalue equation is fully satisfied, and the energy of this particle in 1D box is exact and very precise, and this value is n square, pi square, h cross square divided by twice l square. The second property, square of the linear momentum eigenvalue, px square. px square cap sin x equal to px square cap and psi x equal to px square cap. The eigen operator is minus h cross square and d2 by dx square, and this is the function. But this is double differentiation of this one, we will get the same function. So this eigenvalue equation is fully satisfied in this case also. So when you are doing this mathematics, then it will give you the n square, pi square, h cross square by n square sin x. Same function is coming back. So px square, the magnitude of this square of linear momentum equal to n square, pi square, h square by n square. So eigenvalue equation is fully satisfied. For this x component linear momentum px has this property has the operator minus ih cos d by dx, and the function is this one. This one is the function. So naturally it is saying that this operator when operates on this function, this same function will not be coming. So eigenvalue equation is not satisfied. So the exact value of this Px property is not possible to obtain. So we try to calculate this expectation value or the average value of this Px. So average value of Px equal to, according to this postulate number 3, 0 to L psi nx Px cap psi nx dx, and this whenever these values are, this is the function, and this 2yl square of 2yl coming outside the integration and sin n pi x, and this is the operator, and this also again the function, and dx equal to 0. That means the average value or expectation value of this x component in the momentum equal to 0. But this Px square is this one, so Px equal to root over of this one, and equal to plus minus n pi h cross by L. So it is explained in this fashion. This Px is oscillating within the value plus n pi h cross by L to minus n pi h cross by L. So the average value equal to 0. Then another tough equation, the average position of this particle, again x expectation value equal to 0 to L sin nx and x cap plus sin x dx equal to 2yl, again coming outside this integration, and limit, and x multiplied and sine square n by x by L dx equal to L by 2. Already I have derived in my past lectures. So this expectation value or the average value is L by 2. Most expected position of this particle in one-dimensional box is just at the middle point of this box. Then average square of this position of this particle is a tough mathematics, rather I can say. So this expectation value of x square equal to 0 to L sin x square cap and sin x dx. 2yl again coming outside the integration, and this is the limit 0 to L and x square sin square n pi x by L dx. This integration is rather tough, and I ask the students or the learners or to exercise their mathematical practice to solve this limitation integration, and then they put this limit, and it will be n square by 3 minus n square by 2n square pi square. Now I shall consider the last part of this problem, particularly in 1D box. This verification of the Heisenberg uncertainty principles means del Px into del x greater than half h cross from this particle in 1D box. The results obtained for this 1D box will be helpful to verify the Heisenberg uncertainty principle. We have already calculated the values Px square equal to n square 8 pi square h cross square divided by L square. This is the square of this x component momentum, and Px expectation value of Px equal to 0, and expectation value of x equal to L by 2, and expectation value of x square equal to L square by 3 minus L square by 2 n square pi square. So this delta Px in Heisenberg uncertainty principle is the root mean square deviation, means a standard deviation, and it is given as expectation value of px square minus square of this px. It is the average of this px square minus square of this average and whole to the power half. And this one equal to, whenever writing this one, this px square equal to this one and this 0, so the square root, so this will give n pi h cross divided by a. So similarly del x equal to the expectation value of x square minus square of expectation value of x to the power and whole to the power half. And whenever we are putting this one, this x expectation value of x square equal to this one minus this value and minus and this x average x equal to L by 2 and its square means L square by 4. And this L will be common and L is taken outside of this first bracket. So 1 by 3 minus 1 by 2 n square pi square minus 1 by 4. 1 by 3 minus 1 by 4 equal to 1 by 12 and minus 1 by 2 n square pi square whole to the power half. So this delta px into delta x equal to this value is n pi h cross by L, and this value L into 1 by, within bracket, 1 by 12 minus 1 by 2 n square pi square to the power half. So half h cross we can take it, and the remaining portions here multiplying the 4 n square pi square. So this gives the n square pi square and 4 and 12 it is 3, and here 4 n square pi square whenever multiplying this one, this will give you 2. So for any value of n possible values 1, 2, 3, 4, 5 etc. If we take this value of n equal to 1, then it is pi square by 3 minus 2. Pi is 3.14 and its square. So it will be, this term within the bracket is positive and greater than 1. So this del px into del x will be, must be greater than half h cross. It will, this product uncertainty of these two px and x will never be below half h cross. So this uncertainty is verified from this particle deductions from the particle in one-dimensional box. One problem I can here give for these students to exercise, to make an exercise. A particle of mass m is confined to a 1D box with origin at the center and center of the box. The box extends from minus L by 2 to plus L by 2. The potential energy of this box Vx equal to 0 when x is greater than or equal to minus L by 2 and less than equal to plus L by 2, and Vx is equal to infinity whenever modulus of x is greater than L by 2 is outside of this box. This potential energy equal to infinity, inside of this box potential energy 0. So the questions are, write the Schrodinger equation for the system showing separate equations for the inside and outside of this box. So this is very common. Already I have discussed what will be the Schrodinger equation for inside and outside of this box. And this B, assume a solution inside the box of this form psi x equal to a sin kx plus b cos kx. K is similar that we have taken for this value of k square. So here find the correct form by making use of the boundary conditions. Boundary conditions are, whenever x equal to minus L by 2, then also psi equal to 0, and whenever this x L plus L by 2, then also this psi is equal to 0. And third one, derive the energy of expressions for this particle. So it is energy particle is very common. It will be n square pi square divided by 8 ml square. The answer for this B, psi, there will be two solutions for this even value of n and odd value of n. For the n equal to even, this expression psi equal to a sin n by x by n, and whenever n is odd, then psi equal to b cos n by x by l. Now I shall give here another two problems for exercise. Problem number 2. Calculate the energy levels of this pi network in octatetrane C8H10 using particle in 1D box model. To calculate the box length, assume that the molecule is linear and use the values 135 picometer and 154 picometer for CC double bond and CC single bonds. What is the wavelength of this light required to induce a transition from the ground state to the first excited state? So I have shown here the energy levels, and this n1, n equal to 1, n equal to 2, these are the energy values, energy levels, and delta A transition occurs from n4 to n5. So energy difference is E5 minus E4. This one is 25 E1 minus 25 E1 minus 16 E1 equal to 9 E1 equal to 9 A square by 8 M square. These values coming up at 489.5 nm. And the problem 3 you also see here, and here this M 2m plus 3, and you just do these problems by yourself. This is all about this particle in one-dimensional box. Thanks to you all who are watching this video. For this problem 3, linear polyns have a general formula CH2 double bond CH, and within brackets CH double bond CH M CH double bond CH2. Predict the smallest value of M which could make a polymer a color, treating the electrons according to the particle in 1D box model. Assume a value of 0.15 nm for this CC single bond and